Dear students, we'll take some examples in chemical and ionic equilibrium along with hydrogen chapter. So first example, in a reversible reaction A giving rise to B, the initial concentration of A and B are given as small a and small b respectively. At equilibrium, the concentrations are given as A minus x and B plus x respectively. We have to find the value of x in terms of K1, K2, A and B, where K1 and K2 are rate constants of forward and backward reactions. So we'll go to the solution. So we have the reaction as A giving rise to B. The rate constant for forward is K1, rate constant for backward is K2. So initially is A and B. So equilibrium concentration is A minus x and this is B plus x. So what is K equilibrium constant is equal to concentration of B by concentration of A. Equilibrium constant K is also equal to small k1 by k2 is equal to B concentration is B plus x divided by A minus x. Now if I cross multiply, so it's going to be K1 into A minus x is equal to K2 into B plus x. So I multiply K1A minus K1x is equal to K2B plus K2x. So I'll take the terms containing x together. So K1A minus of K2B is equal to x. I can take common. I can write this as K1 plus K2. So x is equal to K1A minus K2B whole divided by K1 plus K2. This is the final answer for this particular question. So details you can make a note of it. So I'll go to the solution part. The answer key is going to be A. K1A minus K2B by K1 plus K2. Answer is A. We'll go to second example. Example 2. In a reaction, so ammonium carbamate is giving N2 plus H2CO and half O2. Four products are being formed. The value of Kp is given as 27 into 2 to the power lambda by 2 at 800 Kelvin. And equilibrium pressure is going to be given as 22 atmosphere. So what is the value of lambda? We have to find out. Okay. So we'll go to solution. We write the equation. NH2COONH4. So on thermal decomposition gives N2 plus 3H2 plus carbon monoxide plus half O2. These are the four products. Let us say a small amount of the solid has been decomposed to give the pressures as, if I say this as X, then this has to be 3x, this has to be again x, this has to be half x. So total pressure is what? X plus 3x plus x plus x by 2. So this will come out to be 1 plus 3 plus 1, 5, 5 and a half, or I can say 11 by 2 x. This is given as 22 atmosphere. So I can cancel this 11 one times, 11 two times. So I can write x is equal to 4 atmosphere. Now this is the first part of the calculation. I get x as 4 atmosphere. Now to find the Kp of this particular reaction. So Kp is the product of partial pressures of all the 4 gases raised to the power of their stoichiometric coefficients. So I'll write in the next slide. So what is Kp? Kp is equal to, so partial pressure of N2, partial pressure of H2 to the power 3, partial pressure of CO, and partial pressure of O2 to the power half. So we know the partial pressures. This is X. This is 3x into whole power 3. This is again X. This is going to be X by 2 to the power half. So we know X as 4. So Kp is equal to, this is going to be 4 into, this 3 into 4 is 12. So 12 cube. This is again 4. 4 by 2 is 2 to the power half. So if you simplify this and divide by 27, because I have to express the Kp value in terms of 27 into 2 to the power lambda. So if I multiply everything and divide by 27, I get this as 27 into 1448.15. So if you express that in 2 powers, so 27 into 2 to the power 10.5. So from this I can say lambda by 2 is equal to 10.5, or lambda equals 21. So answer is 21 for this particular question. So answer is B. We go to the third question. The average person can see the red color imparted by the complex in an aqueous solution if the concentration of the complex is greater than 6 into 10 power minus 6. So what is the minimum concentration of thiocyanate should be maintained in order to detect the presence of 1 ppm of Fe3 plus in a natural water sample? So 6 into 10 power minus 6 is the minimum to require to see the red color, and concentration is 1 ppm. So the dissociation constant or instability constant of the complex is given as 7.14 10 power minus 3, and these are the options given to us. Okay, so we'll go to the solution. So if I write the equation again, FeSCN 2 plus, this dissociates to give Fe3 plus SCN minus. So initial concentration of iron is 1 ppm. So initially if I take, this will be 0. Fe is 1 ppm. So 1 gram by 56 the number of moles of iron, and this is in 10 power 6 ml of water. So divided by 10 power 6 into 10 power 3. This is the molarity of iron in the beginning. SCN is also not there. So at equilibrium, so when I add SCN, some part of iron gets into complexation. The minimum amount of complex is 6 into 10 power minus 6. So complex concentration, I'll take it as 6 into 10 power minus 6. Now out of this 1 by 56 into 10 power minus 3, this is a molar concentration. Minus 6 into 10 power minus 6 will be complex. So remaining is going to be 1 by 56 10 power minus 3 minus 6 into 1 by 6 into 10 power minus 6, and concentration of SCN minus I have to calculate. So I know all the concentration except SCN concentration at equilibrium, so I can substitute in the instability constant. So I'll write it in the next slide. You can make a note of this. So dissociation constant is 7.14 into 10 power minus 3. This is given as, it is dissociation constant Fe3 plus and SCN on the right hand side. Fe3 concentration is 1 by 56 into 10 power minus 3 minus 6 into 10 power minus 6 into SCN concentration whole divided by 6 into 10 power minus 6. So what is SCN concentration equals to? So I cross multiply 7.14 into 10 power minus 3 into 6 into 10 power minus 6 whole divided by 1 by 56 comes out as 1.78 10 power minus 5 minus. So if I convert this as 10 power minus 5, 6 become 0.6 into 10 power minus 5. So 1.78. So if I take out 10 power minus 5 and simplify this value, so it becomes 7.14 into 6 divided by 1.78 minus 0.6 was 1.18 multiplied by 10 power minus 4. So this, if you simplify, you get this as 3.6 into 10 power minus 3, or I can write as 0.0036 molar. So answer should be 0.0036 molar for the concentration of thiocyanate ion at equilibrium to detect the complexation of iron 3 plus as FeSCN complex. So answer should be 0.0036 molar, that is A. We'll go to the example 4. So in this case, it's a heterogeneous equilibrium again. A small amount of ammonium hydrogen sulfide is introduced into the flask containing ammonia gas already at 0.5 atmosphere pressure. Further, the ammonium hydrogen sulfide decompose to give again ammonia and H2S, and the total equilibrium pressure is found to be 0.84 atmosphere. So what is the equilibrium constant for this particular dissociation? Okay, so we'll take the solution. So what is the equation we have? NH4HS gives rise to NH3 plus H2S. So this is solid, these are gases. So initial solid is in excess, we don't require that. So already ammonia is at 0.5 atmosphere pressure, this is 0. So at equilibrium, again solid is not required. So ammonium hydrogen sulfide decomposes to give more ammonia. So let us say X moles of ammonia is formed by decomposition. So ammonia becomes 0.5 plus X, and H2 is also going to be X. Okay, the total pressure is given as 0.84. So total P 0.5 plus X, that is equal to 0.84. So if I take 0.5 to the other side, 2x equal to 0.34. So x is equal to 0.17 atmosphere. I get the amount of ammonium hydrogen sulfide decomposing to give 0.17 atmosphere of H2S and 0.17 atmosphere of ammonia. So total is becoming 0.67 atmosphere of ammonia. So we have to find Kp. We know the pressures of individual gases. Now we have to find Kp. So what is Kp? Kp is equal to partial pressure of NH3 into partial pressure of H2S. So partial pressure of NH3 is 0.5 plus X, that is 0.17 into 0.17. So it's going to be 0.67 into 0.17. So if you multiply, this comes to as 0.1139. So that's the value of Kp. So in the option, if you see, the nearest answer is 0.11. So the answer should be 0.113 atmosphere square. So we'll go to the options. So answer should be B. Okay. Let us go to the next question. Example 5. A solid A dissociate to give gases B and C. According to the equation, A giving rise to 2B plus 3C. So already it is attained equilibrium. At equilibrium, we are introducing some amount of B, keeping the volume constant, such that the new equilibrium pressure of B is 8 by 5 root 2 times of the original total pressure. Original total pressure. So calculate the ratio of initial equilibrium pressure of C to that of new equilibrium pressure of C. Okay, I'll read the question again. A solid A dissociate into two gases B and C in the ratio in the equation. A gives rise to 2B plus 3C. So already it is attained the equilibrium. At equilibrium, we are adding some amount of B and keeping the volume constant, so that the equilibrium pressure of B becomes 8 by 5 root 2 times of its original total pressure. So we have to calculate the ratio of initial equilibrium pressure of C to the new equilibrium pressure of component C. Okay, so we'll go to solution. Options are given: 1:2, 2:1, 8:2, and root 2:8. So we have the equation as A giving rise to 2B plus 3C. So initial equilibrium, let us say the pressure is 2P and 3P. So what is the Kp value? Kp is equal to 2P to the power 2, 3P to the power 3, or I can write it as 2 squared into 3 cube into P to the power of 5. So that is the Kp value, which is not going to change. Now what is given? You are adding some amount of B, so that the new equilibrium pressure of B is 8 by 5 root 2 times of total initial equilibrium pressure. So initial equilibrium pressure is 2P plus 3P, which is equal to 5P. So partial pressure of B at the new equilibrium is 8 by 5 root 2 into 5P. So 5 get cancelled. I'll get it as 8 by root 2P. And this is going to be, say, PC. So what is the new equilibrium? The square of 8 by root 2P and PC whole cube equated to the original equilibrium constant. Okay, so I can write it as Kp will remain same. So 8 by root 2 P whole squared PC whole cube is equal to 2 cube 3 cube into P to the power of 5. So I have to simplify, get PC in terms of P. Okay, you can take down. I'll go to the next slide. So what I can write? PC whole cube is equal to the Kp, that is 2 squared 3 cube P to the power of 5 whole divided by 8 by root 2 into P whole square. So if you simplify this, 2 squared here is 4, 3 cube is 27, then P power 5 whole divided by 8 squared is 64, root 2 whole square becomes 2, that goes to numerator, and here it becomes P squared. So P squared, this becomes P cube. So if I take PC cube is equal to 4 into 2, 8 into 27 by 64 into P cube. Everything is clear cubes. So what I can write, PC is equal to square root, cube root of 8 is 2, cube root of 27 is 3, and this is going to be 4 into P. So 2 times I can write PC is equal to 3 by 2 P. Now originally the initial pressure was PC was say 1 as 3P. Now PC2 as 3P by 2. So it is ratio will be what, nu to 3P by 2 is to 3P is to 3P by 2. So 3P is to 3P by 2, or I can write it as 1 is to half, or it is 2 is to 1. So the answer should be 2 is to 1. Okay, so we'll go to the options. So answer should be 2 is to 1, that is B. Example 6. The reactions PCl5 gas gives rise to PCl3 plus Cl2 and COCl2 giving rise to CO plus Cl2. These are simultaneously attained in equilibrium at constant volume. A few moles of carbon monoxide is introduced into the vessel at equilibrium. So what is the consequence of addition of this CO to the equilibrium? So if I see the solution, if I write the two equation, so what is the first equation? PCl5 gives rise to PCl3 plus Cl2. PCl5 gives rise to PCl3 plus Cl2. Then second equation is COCl2 gives rise to CO plus Cl2. So what we are adding? We are introducing some more amount of CO is added. So if CO is added, the reaction favored in the backward direction. If the backward direction is happening, the partial pressure of Cl2 decreases. If partial pressure of Cl2 or number of moles of Cl2 decreases, for the first equilibrium, you are decreasing the product, so the forward reaction is favored. So because the forward reaction is favored, PCl5 concentration decreases. As a result, PCl5 amount will be less than the initial equilibrium. It's a conceptual question. So we'll go to the solution options part. So you can see PCl5 remain unchanged is wrong. Cl2 will increase is wrong. PCl5 will be decreased is correct. PCl5 increased is going to be wrong. So option has to be C. C is the correct answer. So we'll go to the next question. In SrCl2 6H2, it is to do with the efflorescent and deliquescent behavior. So SrCl2 6H2O solid is changing to SrCl2 2H2O solid with 4 molecules of water going into vapor phase. The Kp is given as 16 into 10 power minus 12 atmosphere to the power minus 4. Now 1 liter of saturated air, the air which is saturated with water vapor at 1 degree Celsius. So 1 liter of air is exposed to a large quantity of SrCl2.2H2O. So what weight of water vapor will be absorbed by this air? So aqueous tension is given as 1 at 1 degree 7.6 star. So what weight of vapor will be taken by the SrCl2 2H2O to get into SrCl2 6H2O? Okay, so we will go to solution. So options given 6.4 mg, 2.3 mg, 3.25 mg and 8.5 mg. So the equation, I have SrCl2 dot 6H2O gives rise to SrCl2 dot 2H2O, both are solids, and 4H2O, which is gaseous. This is solid, this also solid. So what is Kp is equal to P water to the power 4 times. Now what is given? Kp is given as 16 into 10 power minus 12 is equal to P water to the power 4 times. So if you take the fourth root of 16 will be 2 and 12 by 4 will be 3. So 2 into 10 power minus 3 is equal to partial pressure of water. This is the equilibrium partial pressure of water for this particular reaction. Now in the air, 1 liter of air, what is being used, what is the pressure of the water, we have to find out. This is an atmosphere. So this is the first part. So go to the second part. So it is given as 7.6 star. So the vapor pressure of water in air, 7.6 by 760. So it's going to be 0.01, or I can write 1 into 10 power minus 2 atmosphere. So in the equilibrium it is 2 into 10 power minus 3, and here it is 1 10 power minus 2. Definitely vapor pressure of water in air is more. So SrCl2 will absorb the water from the air. So what is the amount of water it is absorbed? So difference in pressures we have to take. So earlier the pressure is 1 into 10 power minus 2. So the PV is equal to nRT I can use. So number of moles of water is equal to delta P into V by RT. So what is delta P? 1 into 10 power minus 2 minus 2 into 10 power minus 3. V is 1 liter. If I take R as 0.0821, temperature is 274. This is the number of moles. So if you want to get the mass directly, I have to multiply this by 18. So if you simplify this value, I will get this as 0.0064 grams. So or I can write it as 6.4 milligrams of water is absorbed by SrCl2 2H2O to get converted into SrCl2 6H2O to bring back the vapor pressure in that air to 2 into 10 power minus 3. So this is the calculation for this particular question. We'll see the options now. So option should be D, 6.4 milligrams. We'll go to the next question, example 8. Two solid components X and Y dissociate to give A and B and C in this particular equation. So X is solid giving A plus 2B, Y is giving 2B plus C. And Kp is given 9 10 power minus 3, 4.5 10 power minus 3. So we need to calculate the total pressure at equilibrium for a mixture of X and Y. So we'll go to solution part. So two equations, X gives rise to A plus 2B and Y gives rise to 2B plus C. So let us say X decomposing to give X or A pressure of capital A, and according to that it should be 2A. If Y is also dissociating, it will give 2B. So it is same equilibrium. So equilibrium pressure of B should be 2A plus 2B. Here also it is 2A plus 2B, and C will be P. So we know the equilibrium constant for both. So first one is A into 2A plus 2B whole squared, that is equal to 9 into 10 power minus 3. Second one, 2A plus 2B whole square into B is equal to 4.5 into 10 power minus 3. If you divide one by the other, so it becomes, I can write as A by B becomes equal to 9 by 4.5 are equal to 2. Or I can write A is equal to 2B. This is the first part. So once I get A in terms of 2B, I substitute in any one of the equation. So I'll go to the next slide for that. Copy this particular solution. So we have the first equilibrium, 9 into 10 power minus 3 is equal to A into A 2A plus 2B, the whole square. Now A is equal to 2B. So 9 into 10 power minus 3, this becomes 2B. 2A into 2B is 2A in sum of 2B. So it is going to be 2 into 2B, 4B plus 2B whole square. So 9 into 10 power minus 3 is equal to 2B. 6B square is 36B square. So if you simplify 9 and 4 times, I can cancel this. So this is 1 into 10 power minus 3 is equal to 8 into B cube. So what is B cube is equal to 1 by 8 into 10 power minus 3, or B is equal to 1 by 8's cube root is 1 by 2 to 10 power minus 1, or 1 by 2 is 0.5. 0.5 is into 10 power minus 1 is 0.05. I get B as 0.05 implies A is equal to 0.1. So I got A and B values. So what is the total pressure? 2A plus 2B plus A plus B. That means total pressure is always equal to 3 into A plus B. So I'll go to the next slide for that. So total pressure is equal to 2A plus 2B for B and plus A plus B. So 3 times A plus B. So A is 0.05 and B is 0.05, A is 0.1. So 1.15 into 3, it becomes 0.45 atmosphere. So that is the answer for this particular question. Total equilibrium pressure over the mixture of two solids at equilibrium is 0.45 atmosphere. So we'll go to the options. Option should be B. We'll go to the next question. Example 9. A flask is initially filled with pure N2O3 having a pressure of 2 bar, and the following equilibria are established. There are two equilibrium. So N2O3 giving rise to NO2 plus NO, and NO is reacting dimerizing to give N2O4. Kp1 is given as 2.5 bar. We have to find out what is Kp2, and also we have to select the right answer from these particular options. So we'll see the options later. First we'll work out the given problem. So we have N2O3 giving rise to NO2 and NO. So what is initial? This is 2 bar 0 0. So at equilibrium, this is 2 minus x, and this is say x because we have one more equilibrium, NO2 giving rise to N2O4. So part of NO2 is converting into dimerized. So 2 minus x means x will be formed. Out of x, y is going to be converted to dimer. NO is x. So here x NO2 is still x minus y. So if y moles are getting dimerized, dimer will be y by 2. Okay. Now what is given? X is given as 1.5. The partial pressure of NO is given as 1.5. That means x equals 1.5. Substitute that. So this will equilibrium pressure for this will become 2 minus x, 2 minus 1.5 is 0.5. This I'll write it as 1.5 minus y, and this is 1.5. So I know Kp1 has 2.5. So what is Kp1? Partial pressure of NO, partial pressure of NO2 by partial pressure of N2O3. Okay. So this implies 2.5 is equal to NO is 1.5. This is 1.5 minus x divided by 0.5. Okay. So I'll go to the next slide. So I'll write it again. 2.5 is equal to 1.5 into 1.5 minus x by 0.5. So if you simplify, this will become 1.25. 2.5 into 0.5 is 1.25 is equal to 1.5 into 1.5 minus x. So 1.5 minus x is equal to 1.25 by 1.5 comes to 0.833. So x is equal to 1.5 minus 0.833 comes as 0.667. Okay. So x is 0.667. So partial pressure of NO is 1.5. Partial pressure of N2O3 is 0.5. Partial pressure of NO2 is 1.5 minus x, that is 0.833 or 0.83, and partial pressure of N2O4 dimer 0.667 by 2. So it's going to be 0.33. So these are the partial pressures of individual gases. Okay. And also Kp2. Kp2 is partial pressure of N2O4 by NO2 whole square, that is 0.33 by 0.83 whole square. So this comes to 0.479. So if you go through the options, okay, these are the options for partial pressure what I've got. So I'll go to the options now. So if you carefully look at it, equilibrium partial pressure of N2O3 is 0.5 bar, which is correct. Equilibrium pressure of NO2 is found to be 0.833, that is 83, and N2O4 is 0.66 by 2, that is 0.33, and we got the Kp2 as 0.479, almost equal to 0.48. So all the statements are correct. Answer should be A, B, C, D. So we'll go to the next question. So for the reaction NH4I solid giving NH3 gas HI gas. So it's heterogeneous equilibrium, solid is giving gaseous product. If pressure is increased at equilibrium, if you increase the pressure at equilibrium, then automatically the partial pressures has to decrease. So the reaction goes in the backward direction. So we have forward reaction takes place, no change in equilibrium position. We go to the next slide. So backward reaction takes place. So I can map A to R. Same way for the reaction nitrogen, hydrogen combine to give ammonia. Volume is increased. Volume is increased means pressure is decreased. If pressure is decreased, according to the equation, you can see higher number of moles in the left hand side. Again, here reaction goes to backward direction. So B also is mapped to R. Then for the equilibrium, H2O, CO, H2 and CO2. So number of moles of gaseous products and reactants are same. You are adding inert gas at constant pressure, there is no effect because number of moles are same on both sides. Equilibrium will remain in the same position. So I have no change in the equilibrium position, so I can map to Q. Then PCl5 gives us to PCl3 plus Cl2. So Cl2 gas is removed from the equilibrium. If I remove the Cl2 gas from equilibrium, obviously it favors the forward direction. So I can map this to P. So A to R, B to R, C to Q and D to P. That is the answer for this. AR, BR, CQ and DP. Go to the next question. A sample of hot water containing 80 ppm of calcium ion is passed through a cation exchange column where all calcium ions are exchanged to H plus ions. So what is the pH of water coming out of that particular column? Okay, so we're having calcium ions and 80 ppm is present. Those calcium ions are exchanged for H plus ions. Okay, so what is the pH of the solution? So to find pH means moles per liter, so I have to assume 1 liter of water has been passed through the column. So if I take the solution part, so 80 ppm I have to convert into molarity. So 80 ppm means 80 grams divided by 10 power 6 grams. So since it is molecular mass is 40 for calcium, so 80 by 40 moles divided by 10 power 6, this is per ml of water, so I have to multiply by 1000. So this will be 2 times and this will be 3 times. So this is equal to 2 into 10 power minus 3 molar. Now you know that each calcium exchanged with 2 H plus ions. Therefore, concentration of H plus becomes 4 into 10 power minus 3. So what is pH? 3 minus log you have to take. So 3 minus log 4. Log 4 is 0.6990, 0.6021, 0.6 I can take. So it's going to be 3 minus 0.6, it's going to be 2.4. So pH of the solution or water coming out of the exchange column will be 2.4. We'll go to the options. Answer should be D, that is 2.4. Example 12. 100 ml of 0.001 molar HCl is added to 1 liter of HA, weak acid. You are adding a strong acid to weak acid. So there is a common ion effect. So due to common ion effect, the degree of dissociation of HA, that is weak acid, is decreased. So degree of dissociation of HA will decrease. That is one of the correct options. Which of the following is correct? So degree of dissociation of HA will decrease, but pH will remain same? No, because you are introducing a strong acid, it furnishes lot of H plus ion. Because of H plus ion concentration is increased, the dissociation of HA is decreased. So degree of dissociation of HA definitely decreases, and along with H plus concentration is increased, so pH also will decrease. So both pH and degree of dissociation of HA will decrease. That is the right answer. If you see the B option, degree of dissociation of HA increases, pH decreases, which is wrong. Neither pH nor degree of dissociation decreases, also wrong. This also wrong, and this is the right answer. It's a conceptual question. So when you add a strong acid to a solution of weak acid, definitely degree of dissociation of weak acid decreases, also pH will decrease. So option D is the answer. Next question. In terms of K1, K2, K3 of a weak triprotic acid, the value of Kb of BH2 minus is BH2 minus is. So if you take the three dissociations, so H3B gives rise to H plus BH2 minus. So this is Ka1. Same way, BH2 minus gives rise to H plus BH2 minus. This is K2. Then finally BH2 minus gives rise to H plus B3 minus. This is K3. They're asking for Kb of BH2 minus. So if I take BH2 minus here, this is the conjugate base of H3B. So Kb is equal to Kw by K. So all of us know for a conjugate acid base pair, Ka into Kb is equal to Kw. So Kb is equal to Kw by K1. If it is this, then Kb is equal to Kw by K2. If it is for B3 minus, then Kb is equal to Kw by K3. So whichever is asked, you can get the answer. BH2 minus will be this, BH2 minus will be this, and B3 minus will be this. So we'll go to the options. So answer should be B. In says is BH2 minus. So answer should be Kw by K2. In the question it was BH2 minus. In that case it should be option A. So whichever is given you can answer. Answer is B for BH2 minus. We'll go to the next question. A sodium salt of certain weak monobasic organic acid is hydrolyzed to an extent of 3% in its 0.1 molar solution. The dissociation constant of the weak acid. It is based on the hydrolysis concept. So 3% and 0.1 molar. So we'll go to solution part. So alpha is 3% means 0.03. C is equal to 0.1. So all of us know alpha is equal to root of KH by C. So if you substitute 0.03 is equal to root of KH by 0.1. So square both sides. This will be 0.03 square means 9 into 10 power minus 4 is equal to KH by 0.1. So what do I get for KH? KH is equal to 9 into 10 power minus 5. So I know that KH is equal to KW by KA, or KA is equal to 10 power minus 14 by KH, that is 9 into 10 power minus 5. So if you simplify, this will become approximately 1.1 into 10 power minus 10. So 1 by 9 is 1.1 and 10 power minus 10 will be the power. So if we go to the options, So 1.1 is not there. Option B is the nearest. 1.1 into 10 power minus 10. So power is important than the number. So answer is going to be B. So 1.1 10 power minus 10 or approximately 1 into 10 power minus 10. Example 15. Which of the following order of pH of 0.1 molar solutions of following solutions are correct? So we know due to hydrolysis, the salt of strong acid, strong base will be definitely neutral. The pH will be equal to 7. The salt of weak acid and strong base will have higher than 7 because strong base is going to be dominating. And the salt of weak base and strong acid will be less than 7. So if you carefully look at the given options, you have HCl, NaCl, HCN and NaCN. So HCl, NaCl, ammonium chloride and NaCN are given. So if I take HCl, HCl is a strong acid, so there is not a salt. Then NaCl is neutral, pH is equal to 7. NH4Cl coming from NH4OH plus HCl. So it is strong and this is weak. So it is pH will be less than 7. And NaCN is coming from NaOH plus HCN. This is weak, this is strong, so pH will be greater than 7. So this is much less than 7. So this is the least. So HCl should be the least. Then it is ammonium chloride. Then it is NaCl, which is neutral. Then it is NaCN. This is the order of pH. So if we choose from the options, so if you see HCl is C and D, these two are ruled out. So HCl, NaCl is not the one, NH4Cl. So this is the right answer. This is wrong. Answer should be D. Next example, self-ionization constant of formic acid is given by this formula and it is equal to 1 into 10 power minus 6. It is similar to ionic product of water, it is ionic product of formic acid. So density is given as 1.15 10 gram per cc. So asking for percentage formic acid in the pure acid converted to formate ions. How much of formic acid molecules by percentage by mass converted into formate ions. Okay, so we'll go through the solution part. So we have the equation 2HCOOH decomposed to give HCOOH2 plus and HCOO minus, autoionization of formic acid. So in pure formic acid, these two will be equal. So HCOOH2 plus is equal to HCOO minus. It is equal to 10 power minus 3 because K is equal to 10 power minus 6. So product is equal to 10 power minus 6. So equal, that means each of them should be 10 power minus 3. Now what is the concentration of HCOOH we have to find out. So concentration of HCOOH in the pure form. So I have to find the number of moles in 1000 ml. So 1000 ml means 1000 into density, that is 1.15, that is mass of formic acid divided by 40. Like what we do for water, 1000 by 18. So it is 1000 into 1.15 by 40. So this comes to 25 moles. So there are 25 moles in 1 liter of formic acid. Out of these 25 moles, only 10 power minus 3 moles are converted into formate ion. So percentage conversion is equal to 10 power minus 3 divided by 25 into 100. So this, if you calculate, it becomes 0.004%. 25 into 4, this is going to be 4 into 10 power minus 3 is going to be 0.004%. So that is the conversion of formic acid into formate ions in pure formic acid. So answer should be D. Sorry, should be B, not D. It should be B, 0.004%. So it was wrong, it is B. Example 17. 100 ml of buffer containing 0.1 mole of HA and 0.2 mole of NaA is mixed with 100 ml of another buffer containing 0.2 mole HA and 0.3 mole NaA. What is the pH of resultant buffer solution, and pK is given as 5. So first we'll take the two buffers. First one 100 ml, 0.1 HA, 0.2 NaA. So buffer 1 HA, number of moles will be 100 into 0.1. From second buffer I am getting 100 into 0.2 whole divided by 200. That is the concentration of H in the resultant buffer. So this is going to be 10 plus 20, 30 by 200. Same way if I take NaA, so it is going to be 100 into 0.2. Second buffer 100 into 0.3 divided by total volume 200. So 20 plus 30, 50 by 200. So we know that pH is equal to pKa plus log of concentration of NaA by HA. So this is equal to 5 plus log 50 by 200, 30 by 200, 200 cancel, 0 cancel. I will get this as 5 by 3. So this is the value for pH of the buffer which is obtained after mixing. So if you go through the options, pH is equal to 5 plus log 5 by 3. Option B is the right answer. Question number 18. An acid-base indicator has a pKin of 5.45. At what concentration ratio of sodium acetate and acetic acid would the indicator show a color halfway between its conjugate acid and conjugate forms? pK of acetic acid is given as 4.75. So there are two pK values given. One is pKin of indicator, another one is pKa of acetic acid. So we are adding the indicator to the buffer which is acetic acid and sodium acetate. So the question is, at what ratio of acid and salt or salt and acid concentration the buffer, the pH indicator will show color halfway through its conjugate acid and conjugate base. So we go to solution. As per the indicator equation, pH is equal to pKin plus log of In minus by HIN. So at halfway pH is equal to pKin. So which is equal to 5.45. So this is the pH. Now we have to substitute this pH in the buffer equation of sodium acetate and acetic acid. So for buffer I can write pH is equal to pKa plus log of salt by acid. So 5.45 pKa of acetic acid is 4.75 plus log of salt by acid. So if you find the concentration, 5.45 minus 4.75 is going to be 0.7 is equal to log of salt by acid. So log 7, antilog of 7, log 5 is 0.7, 0.6990. So I can approximate as 5. So 5 is equal to salt by acid. So the answer should be salt is to acid is equal to 5 is to 1. That's the ratio of concentration of salt and acid, 5 is to 1. So we'll go to the options. So answer should be C. Question number 19. The solubility product of barium chromate BaCrO4 is 2.4 10 power minus 10 molarity square. What is the maximum concentration of barium nitrate possible without causing the precipitation from this particular potassium chromate solution? So we'll go to solution. So Ksp of barium chromate, so Ba2 plus into CrO4 2 minus is equal to 2.4 into 10 power minus 10. So what is the concentration of barium? We have to find out what is the maximum concentration. Potassium chromate is given as 6 into 10 power minus 6. So K2CrO4 is given as 6 into 10 power minus 6, means CrO4 2 minus is also 6 into 10 power minus 6. So what is Ba2 plus concentration? Ba2 plus is equal to 2.4 10 power minus 10 divided by 6 into 10 power minus 6. So this will become 0.4 into 10 power minus 4, or the maximum allowed barium plus concentration will be 4 into 10 power minus 5. Anything above this value, there is a precipitation of barium chromate. So if you see the options, which one is below this or equal to this? If you see the option, so 10 power minus 10, that is lesser but not the maximum. They are asking for maximum concentration. So 10 power minus 4 and 10 power minus 4 here is ruled out. So 4 into 10 power minus 5 is what is required. So this is the maximum. This is too less. This will be maximum possible concentration among the given options. So answer should be A. So we'll go to question number 20. When pure water is saturated with calcium carbonate and calcium oxalate, so both the salts are added to pure water, so that both become saturated. It's a simultaneous solubility. The concentration of common ion, this calcium ion, is given as 8 into 10 power minus 5. And if the ratio of solubility products of two salts is 3, then what is the solubility of calcium carbonate in pure water, not in the mixture? So I have to get Ksp of calcium carbonate. So what we'll do now, go to solution. So pure water is added with calcium carbonate and calcium oxalate. We'll try the two equations. So CaCO3 gives rise to Ca2 plus CO3 2 minus. Same way, CaC2O4 gives rise to Ca2 plus C2O4 2 minus. So let us say from calcium carbonate, this is X and this is X. Calcium is common, so I can write here Y is coming from calcium oxalate. So I am writing it as X plus Y into Y. So we know KSP is common calcium ion concentration is nothing but X plus Y, which is given as 8 into 10 power minus 5. And if you divide by the KSP values of both, I can get cancel calcium concentration cancels out. X by Y I can get as 3. So if you take the ratio of two KSP values, then X plus Y get cancelled. I get X by Y as 3. So implies X is equal to 3Y. Substitute this in one of the KSP value, calcium carbonate. So KSP of calcium carbonate is equal to X plus Y into X. So X is equal to 3Y. First we have to get either X or Y from one of the equation. So we know that X plus Y is equal to 8 into 10 power minus 5 and X by Y is equal to 3. So substituting X as 3Y in this calcium concentration before we go for KSP. So X is 3Y. So I can write 3Y plus Y is equal to 8 into 10 power minus 5. So 4Y is equal to 8 into 10 power minus 5, or I can write Y is equal to 2 into 10 power minus 5. So this is the value of Y I will get. So X I can get 2 into 3 will be 6 into 10 power minus 5. Now if I go for KSP of calcium carbonate, okay, I'll go to the next slide. So KSP of calcium carbonate is X plus Y into X. So we know that X is 3Y. So 3Y plus Y into 3Y. So 3Y, 1Y. So 4Y, 4 into 3, 12Y. 12Y square. So Y we know that 12 into 2 into 10 power minus 5 whole square. So 12 into 2 square is 4. So 48 into 10 power minus 10. This is KSP of calcium carbonate. So in pure water, solubility is equal to root of KSP. So root of 48 into 10 power minus 10. So closely 49 is 7 square. So it may be around 6.9 10 power minus 5 molar. This is the concentration of solubility of calcium carbonate in pure water. Okay, we'll go to the options. So 6.9 10 power minus 5, option D is the answer. We'll go to question number 21. A solution of sodium carbonate is added drop by drop to 1 liter solution containing barium ion and silver ion. It's a selective precipitation concept. If KSP of both the salts are given, which the following statement is are correct. Okay. So no precipitate of barium carbonate will appear until this one. So a precipitate of HgCO3 will appear which 6.9 10 power minus 5. Some concentrations are given which will precipitate first. So we'll first find out what is the concentration of carbonate ion required to precipitate both salts and which will precipitate first. So we'll go back to the slide again. So KSP of barium carbonate is 8.1 10 power minus 9 and Ag is 6.9 10 power minus 12 and barium concentration is 10 power minus 4, Ag is 10 power minus 5. So barium concentration is 10 power minus 4 and Ag plus concentration is 10 power minus 5. So what is KSP given? Ba2 plus into CO3 2 minus is equal to 8.1 10 power minus 9. So if we substitute this 10 power minus 4, CO3 2 minus is equal to 8.1 10 power minus 9 by 10 power minus 4. So 8.1 into 10 power minus 5. Same way for silver. So Ag plus whole square into CO3 2 minus is equal to 6.9 10 power minus 12. So the Ag is 10 power minus 5. So CO3 2 minus is equal to 6.9 10 power minus 12 divided by 10 power minus 5 squared is 10 power minus 10. So this comes to 6.9 10 power minus 2 molar. So if I see the concentration, this is lower. So BaCO3 will precipitate first. So this is the concentration required. So for barium it is 8.1 10 power minus 5. For silver carbonate it is 6.9 10 power minus 2. So we'll go to the options. No precipitate of barium carbonate appear until carbonate concentration is 8.1 10 power minus 5, which is a correct statement. A precipitate of Ag2CO3 will appear when CO3 is 6.9 10 power minus 5, which is wrong because the minimum required is 6.9 10 power minus 2. This is less than that, so you cannot get a precipitate. No precipitate of Ag2CO3 will appear until CO3 is 6.9 10 power minus 2, which is right, and barium carbonate will precipitate first. So answer should be A, C and D. B is the wrong statement. Example 22. What is the maximum pH required to prevent the precipitation of zinc sulfide from a solution of 0.01 molar ZnCl2 when saturated with 0.1 molar H2S? So KSP is given and the total Ka of H2S is given. Okay. So first we have to find out what is the sulfide ion concentration required to precipitate ZnS, and that sulfide ion concentration should be substituted in dissociation constant of H2S. So we will take the solution. So KSP of ZnS. So Zn2 plus into S2 minus is equal to 1 into 10 power minus 21. So zinc concentration is given as 0.01. So S2 minus concentration 1 into 10 power minus 21. So concentration of sulfide ion required is 1 into 10 power minus 19 molar. So anything above this can precipitate ZnS. So if I want to find out the concentration of sulfide ion should be less than this, I need to maintain H plus ion concentration by adding HCl, right? So I have to substitute this in H2S. What is the minimum pH I have to require? So I'll go to the next slide for this. So H2S dissociates to give 2H plus S2 minus. So overall Ka is given H plus ion square into S2 minus by H2S. So K is given as 10 power minus 20, H plus ion concentration whole square, I don't know. Sulfide I calculate 110 power minus 19, this is going to be 0.1. So 19 get cancelled, this becomes minus 1, 0.1. So I get H plus ion square is equal to 0.01, or H plus is equal to square root of 0.01 is 0.1 molar. So pH is equal to 1. So the pH should be 1. If the pH is less than 1, it is going to be not precipitating the ZnS. If pH is more than 1, H plus is less than 0.1 molar. So definitely sulfide ion is more than 10 power minus 19. So answer should be pH is equal to 1. So answer should be B. Question number 23. In context with industrial preparation of hydrogen from water gas, which of the following statement is correct? So, CO is removed by absorption of aqueous CO2Cl2 solution. H2 is removed by occlusion with palladium. CO is oxidized to CO2 by steam in presence of a catalyst and absorption by alkali. CO and H2 are fractionally substituting difference in their densities. So, according to the industrial preparation of hydrogen, the water gas produced is made to undergo oxidation. Carbon monoxide is converted to CO2 in presence of a catalyst, and the CO2 is absorbed by alkali, and the CO part is completely removed and hydrogen is obtained. That is the industrial method of preparing hydrogen starting from water gas. So, option C is a conceptual question. Answer C should be the right answer. Example 24. The temporary hardness of water containing magnesium bicarbonate is boiled and it forms a precipitate of. Again, this is a conceptual question. So, for calcium bicarbonate, when you heat, it converts into insoluble calcium carbonate. But remember, for magnesium hydroxide, magnesium bicarbonate, when you boil, it precipitates magnesium hydroxide rather than magnesium carbonate. Magnesium carbonate is more soluble compared to magnesium hydroxide. So, magnesium hydroxide is precipitated, not magnesium carbonate. But calcium bicarbonate, when you heat, it converts into calcium carbonate. So, answer should be A in this particular question, not magnesium carbonate. Question number 25. Which of the following is incorrect? So, ionic product of D2O is greater than H2O. Solubility of inorganic substance more in H2O than D2O. Mass of D2O is more than H2O. Enthalpy of fusion is D2O has more than H2O. Now, mass of D2O definitely greater than H2O. So, it is a correct statement. And water is more polar compared to D2O. So, solubility of inorganic substance more in water compared to D2O. Then ionic product. Ionic product is nothing but dissociation of water into H plus and OH minus. So, you have to break that OH bond. So, if you want to break the OH bond, OD bond is stronger than OH bond. So, dissociation of D2O is less compared to dissociation of water. As a result, ionic product of water is slightly more compared to ionic product of D2O. So, this is the answer. This is a wrong statement. They are asking for incorrect. So, option A should be the answer. Example 26. Identify the incorrect statement with respect to hydrogen peroxide. So, hydrogen peroxide is prepared by acidifying barium peroxide and hydrolyzing by H2S2O8 and H2SO5. H2S2O8 is peroxy disulfuric acid, H2S2O5 is peroxy monosulfuric acid. If you hydrolyze them, you get H2O2, and barium peroxide on acidification, you get hydrogen peroxide. Option A is a correct statement. It is thermodynamically stable. So, H2O2 can decompose. If I take a bottle of H2O2, keep it for some days, I will end up with only water in it. So, H2O2 spontaneously decompose to give H2O and O2. It is relatively less stable. So, this is the wrong statement. It has a non-polar structure. That is also correct. It can act as an oxidizing as well as reducing agent. So, in open book structure of H2O2, the dipole moment get cancelled. It is a non-polar structure, and oxidizing and reducing agent both are shown by H2O2. So, answer should be B. It is thermodynamically less stable. Answer should be B. Question number 27. Which of the following statement with respect to hydrides is not correct? So, ionic hydrides are crystalline, non-volatile, non-conducting in solid state. So ionic crystals are going to be, ionic compounds are crystalline, ionic hydrides are also going to be crystalline in nature. They are non-volatile substance and non-conducting in solid state. So statement 1 is correct. Electron deficient hydrides act as Lewis acids. Very correct. Electron deficient compounds will act as Lewis acid. Even hydrides also will act as Lewis acid. The example is BH3. So group 13 elements form electron deficient hydrides. That is also correct. Elements of group 15 to 17 form electron precise hydrides. Electron precise hydrides means there should not be any lone pair on the central atom. So group 14 elements, carbon, CH4, SiH4, these are going to be electron precise hydrides, but NH3, PH3, nitrogen, phosphorus has one lone pair, H2O, oxygen has two lone pair, so they are not electron precise or electron rich hydrides. So option D is the wrong statement. So answer for this particular question is D. Question number 28. How many milliliters of perhydrol is required to produce sufficient oxygen which can oxidize 2 liter of SO2 at STP? So if you recollect the meaning of perhydrol. So perhydrol is 100 volume H2O2. That means 1 cc of H2O2 gives 100 cc of O2 at STP. Now what is required for us? SO2 plus O2 gives SO3. So 2 SO2, 2 SO3. I have 2 liter of SO2. I require 1 liter of oxygen. So if I want to require 1 liter of oxygen, so 100 cc is obtained by 1 cc. So 1 liter means 1000 cc. So 100 cc of oxygen from 1 cc of H2O2. So 1000 cc from how much? So I'll get exactly 10 ml. So 10 ml of perhydrol can give 1 liter of oxygen at STP, which is sufficient to oxidize 2 liter of SO2. So answer should be, we'll go to the options. Answer should be 10 ml, that is option A. Okay, dear students, these are some of the examples what I thought I'll discuss in chemical and ionic equilibrium and hydrogen chapter. Thank you.